Determinants, adjoint matrices, Cramer's rule, and their uses. First off, what is an adjoint matrix? An adjoint matrix is a matrix that can be derived from another one, known as the original matrix. Both of these have the same dimensions and must both be square. There are many matrix operations and properties that require adjoint matrices that we will detail in this video. First, we need to know how to find an adjoint matrix. There is a very simple three-step process for doing this. First, find the matrix of minors, then the cofactor matrix, then finally the transpose. The first step is to find the matrix of minors. The definition of minor is the determinant of the matrix created by all terms that don't share a row or column with the given term of the original. As you see here, the term we're starting with is a sub 1, 1, so we cancel its row and column to find the determinant of the remaining four terms. The resulting matrix of minors can simply be represented as shown here, where all terms are denoted by the letter M. Next, we find the cofactor matrix. This is the same as the matrix of minors, except some terms are replaced with their opposite. This is done according to the sign matrix. The 3 by 3 sign matrix is shown here, and it shows that 4 out of 9 terms must be replaced with their opposite. So we can see that the cofactor matrix is found when the 1, 2, 2, 1, 2, 3, and 3, 2 terms of the matrix of minors are replaced. Finally, we need to find the transpose of the cofactor matrix, which is very simple. Just flip the matrix so that its rows turn into its columns and vice versa. And now, the resulting matrix is the adjoint matrix. Before we get into the use and properties of adjoint matrices, we have to go over their notation. C represents the cofactor matrix, and C with a subscript represents the cofactor of a certain term within the original matrix. The same goes for the matrix of minors, except using M instead of C. A superscript of T represents the transpose of a matrix. DET represents the determinant of a matrix, and ADJ represents its adjoint. Finding the inverse of a matrix can be very simple using adjoints. First, find the determinant and the adjoint of a matrix. Then multiply each term of the adjoint by 1 over the determinant, and there you have it, that's your inverse. Here are some important properties of adjoint matrices. One of these properties is that the adjoint of the identity matrix is the identity matrix. Another one is that the adjoint of A times B equals the adjoint of B times the adjoint of A. Keep in mind that the order has switched here. Another property is that the adjoint of scalar C times matrix A equals C to the n minus 1 times the adjoint of A, where n is the dimensions of A. In addition, the adjoint of A to the m power, close parentheses, equals the adjoint of A, close parentheses, to the m power. And finally, the adjoint of the transpose of A is the transpose of the adjoint of A. Keep in mind that this basically means that the cofactor matrix of A is equal to the cofactor matrix of A.
Alright, Cramer's rule. So, Cramer's rule is a method that can be used to solve for all of the variables in a system of equations, or you can use it to solve for only one variable in a system of equations. So if you're doing an exam or a problem where it only asks for one variable, or you have a real-life situation where you really only need to know one thing and you don't really care about the other things, then it makes it, you don't have to solve for them, you can just solve for one. So the notation for Cramer's rule, it's pretty basic. If you put your system of equations in the form Ax equals B, A is your coefficient matrix, B is your answer column, then D is just a determinant of your coefficient matrix, and for DI, this is really the only slightly complicated one. It's not really that complicated anyway, but for DI, it's the determinant of the coefficient matrix. However, it's after you take the column of the I variable and you replace it with the answer column of the system of equations. So Cramer's rule says that if you have the variable I, it is equal to DI, where you're taking that coefficient matrix and replacing that I column with the answer column, divided by the determinant of your coefficient matrix by itself. So solving a 2 by 2 system, in the general case, you're just taking the determinant of your coefficient matrix, ABCD, which is going to be AD minus BC, and then you're taking your coefficient matrix again to find dx, but you're replacing that AC in the x column with EF. And you're taking that determinant, which gets you ED minus BF. And then for dy, you're just replacing that y column, BD, with EF, and you're coming up with AF minus EC. So then using Cramer's rule, we're saying x equals dx over d, which is ED minus BC over AD minus BC, and then you're saying y equals dy over d, so AF minus EC divided by AD minus BC. So solving a 3x3 system of equations is very similar. It's basically the same thing. So you have your system of equations: x plus y plus z equals 1, x plus 5y plus 4z equals 0, xy plus 2y plus 2z equals negative 1, and you're just saying your coefficient matrix here: 1, 1, 1, 1, 5, 4, 1, 2, 2, and then your answer column is b, 1, 0, negative 1. You're taking your determinant of your coefficient matrix. You're not doing anything to it. You're just taking the determinant. You do out all that icky arithmetic, and you get to 1. And in these examples, the determinant of your coefficient matrix, it worked out to 1 both times, which is really neat and nice because it means we get to put d in the denominator. When we do I equals d of I over d, I didn't plan that, it just happened, so that's cool. But it won't always work out that nicely. So then you're going to do the same thing for each of your DIs. So dx, you're taking that 1, 1, 1 in your x column, and you're replacing it with a 1, 0, negative 1 from your answer column. And d of x just has parentheses around it. It's supposed to have the determinant symbol. That's another typo on my part. But that comes out to 3 when you do out all that math. So then you're doing the same thing for dy and dz. For dy, you're taking out that 1, 5, 2 in the y column. You're replacing it with 1, 0, negative 1. And then for dz, you're doing the exact same thing. You're taking out that z column of 1, 4, 2 and replacing it with your 1, 0, negative 1 of the answer column. So when you do all the work, dy comes out to 5, dz comes out to negative 7. So now we're using Cramer's rule again here. X equals d of x over d. So x is just going to be 3 over 1, which is 3. Y is going to be dy over d, which is 5 over 1, which is 5. And then z is going to be d of dz over d, which is just going to be negative 7 divided by 1, which is negative 7. So those are two examples with Cramer's rule. Solving a 2x2 and solving a 3x3 are very similar. 3x3 is just a little bit more complicated because there's more to do to find the determinant, and there's more variables to solve for. So now, because of the way it's set up, Cramer's rule works, you can solve for only one variable. So if we go back to our 3x3 example, if we only wanted to solve for x in this situation, we wouldn't have had to find dy and dz. We'd have only had to find d and dx, and then we'd have just been able to say x equals dx over d equals 3 over 1 equals 3, and we'd be done. So it would be much simpler. And Cramer's rule is also very fast for 2x2 matrices. If we go back a couple slides to our solving a 2x2 system, all we did was we quickly scribbled down the coefficient matrix, found its determinant really quickly, and then we found d of x and d of y. We just scribbled down the numbers again, except just replacing that x and y column with the answer column when in their respective places. We found 3 and 5, did a quick division, and we have our answer. So that is also a benefit. However, when we look at our 3x3 solving a system, it takes a while to solve for the entire system. So if you have a more complicated coefficient matrix, or like if you have access to a GDC, plug it in reduced row echelon form in the math section, like way simpler. If you don't have a calculator, this works if it's fairly simple. It came out really nicely because D is 1, so it was a very simple division there. With more complicated matrices, it may be easier to use that adjoint method to solve, where you just take your coefficient matrix and you find the adjoint and then just multiply it by the determinant to find your inverse, and then just solve using matrix methods. So that's a drawback for Cramer's rule, and yeah, that's pretty much it. So this is Cramer's rule and the adjoint method, and yeah, thanks for watching.